Okay, let's get going here. I heard 6 bells. That's enough for me. If we go to the course outline and we go to our approximate schedule, let's see where we are with this. Last session, we talked about the reduction of digital logic and began Kernel mapping. So we'll probably get to Unit 6 tonight. I don't know if we'll finish it or not, but we have a little more to do on the Kernel maps as well as reduction. We were behind a little on the transistors, which is fine. We'll catch up. There's some built-in slack down here a little later to make up for that. And so looks like we're about Unit 6 if you're keeping track of that sort of thing. You know, some of you keep your eyeball right here on exam 1 because you know that's where, you know, the rubber meets the road. Also, one of the things I want to point out to you is our next unit, we're going to cover the last bit of stuff we're going to do with combinational logic for a while. And we're specifically going to apply some of the transistor circuit knowledge to talking about some integrated circuits that actually use that technology. So this should be a very interesting session. Digital components are kind of the application of what we've been doing. Right now, we've been just arbitrarily writing down zeros and ones without them really having any reason for being there. But once we start, you know, giving them meaning, and we kind of build little units of work that we could later come back to and say, well, in our microprocessor, we're going to need something that knows how to do X. And we already know how to do that because we have, at least in our minds, designed a digital component that knows how to do that. Would be, you know, kind of like if you went in your kitchen and you found all the little flat pieces of metal you had, or close to flat pieces of metal, and then later learned that there was a knife, a spoon, and a fork, and they had some sort of specific purpose. It's the same sort of idea we're going to have here with combinational logic, is that some of the ideas and notions we've had actually have meaning. We just haven't called out the meaning yet. So we'll go back, and we're working on Kernel mapping right now because we have a little more to learn there, and see if we can get into some Quine-McCluskey as the evening goes forward. So the question was raised, given this truth table, and given a blank Kernel map, which we could use to solve the problem, what is the minimum sum of products equation? Basically, what does y equal in a minimum way to describe the function that's illustrated by these ones and zeros? Zeros meaning false, ones meaning true, or some other dichotomous notion that we have taken care of. Notice, please, that if we were to write this out completely using minterms or fundamental products, for every place we have a 1 under the y, we'd have a 4-term equation. So just starting that out, we would have something that would start out like y is equal to not A, not B, not C, not D, or let's move on to the next one. Well, it's not A, not B, not C, D. Or, and if you notice, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 terms. There'd be 11 4-input terms to evaluate to y. Now, what we're hoping is we can do better than that because it'll cost us less to build the circuit. It'll use less power, generate less heat. We'll have shorter distances for the current to move in order to speed up the ability to implement this function. And basically, we'll analyze the functions to see if there's any redundant data in there. Maybe there's some terms and things we don't even need. But we could do this using algebra. We'll review some of the algebra again in a few minutes. But right now, let's use a Kernel map. Kernel map, as you recall, has to have the same number of squares in it as there are lines in our truth table. We have a 4-input truth table. So that means we have 2, oops, where'd my pen go? We have 2 raised to the number of inputs number of rows. So 2 raised to the 4th is 16. So we have 16 rows. They'll be labeled 0 through 15. This is 0. This is 15. So we're going to need 16 places to put our 1s or 0s. And we're going to put them in a way that's systematic, meaning that we're going to start at this corner and we're going to put into the next box in any direction that's horizontal or vertical, not diagonal, but horizontal or vertical, in such a way that there's only a single bit change between the two boxes. So between this box and that box, we're going to see the only change is D has gone from inverted to not inverted. Between this box and this box, the only change we're going to have is C is going to have changed between inverted and not inverted. We go from this box to this box. We're going to see that only D has changed from D to its inversion here. And if we wrap around to the other end, the difference between this and this are only that C has changed. It's gone from not inverted to inverted. So this spot right here is attached to that spot right there. And we can do the same thing vertically. The difference between this square and this square is only that B has changed. Difference between here and here is only that A has changed. Again, difference from here to here is B changed. And the difference from the bottom up to the top is that A changed. So by moving a single box in our Kernel map in a horizontal or vertical direction, we have a single bit changing. Now, if we were to look at the data over here, we'd see between the first row and the second row, 1 bit has changed. We'd see between the second bit, however, second row and third row, 2 bits have changed. This 1 changed to a 0, and that 0 changed to a 1. However, if we went from this guy down to this guy, there would only be a single bit change. It would be the second to last bit. And we then could come back up and catch the third guy because between here and here, there's only a single bit, and then go to the next grouping in such a way that only a single bit has changed. But of course, here we see that we have 2 bits actually changing between this and that row. So we have to deal with that as we move through the table. We talked about the order if we were to then sit down and number the boxes. Fill this box, this box, this box, that box, this box, this box, this box, this box. Now we have a huge change between these two rows, if you see. So we would have to jump down here to get the 9th, the 10th, the 11th, and the 12th. And then finally, 13, 14, 15, and the 16th box. And you notice the 16th box is really A, B, C, D, or 1, 1, 1, 1, which is 15. But we didn't start with 0. We started with 1, so we'd expect to go from 1 to 16 rather than 0 to 15. We could have numbered it either way, and it would still made sense. But that little hop skip we do every third element and also every third row are very important, making sure that we fill the table in correctly. Let's go back a little ways here. And let's take our table and let's fill it into the Kernel map. I'm going to first of all divide the table into sets of 4 just because this is easier on my eyeballs. It's not necessary that you do that, but I find it is easier to read the elements. Okay, Gabriel, what's the first row going to look like? Okay, we're going to transfer this data into this row. Kyle, you want to help him out?
The first would be
One of you has background noise. I think it's you, Gabriel. Okay, Kyle, what's it going to be? Where are these going to go?
so the first would be the not A, not B, not C, and not D in the first box.
And what would I put there?
The one.
Would I put a 1 or a 0? 1?
One.
Okay. What's in the next box?
Wouldn't it be the so not A, not B, not C, but D, so 1 again?
Okay. Now we go over to the right-hand column because that's the one that matches this row. And there'd be a 0 there, right? But we never write zeros in. And then the last one in that set goes here. So remember the ordering. First column, second column, fourth column, third column. Okay. Robert?
Sure.
Robert, help me out with the next row. What's the next row going to do?
It's going to be 1, 1, and then you go to the fourth spot, which is blank. Oh, not blank, sorry, it's a 1.
Okay, and then the last square.
Which is blank.
Okay, it's a 0, right?
Yeah.
Okay. Ryan, what are we going to do in the last row now? It's going to be the next set.
I apologize. I'm having trouble following this. I'm still trying to figure it out.
Okay, Oscar?
So like the third set would go in the fourth row?
Right. And what's the value I'm going to write in this box? 0 or a 1?
Blank.
Well, it's a blank, but it implies 0. Okay.
Yeah. Right.
And then here?
1,
Okay.
and the rest
Now we
are
jump
1.
over the fourth column. Well, we'll do them in order. And then we drop to the fourth
Yeah.
column for the next one.
1.
And then we come back here for another one.
Yeah.
Okay, now we're on the last row. Thomas?
It would be blank or 0, 0,
Okay.
and then 2 1s.
1. And final square is there. Last row is right here. Okay, so now we've got all our 1s in our table. Okay, so what we want to do now is we want to try to do graphic reduction on this. What we're going to look for is in powers of 2 from the biggest to the smallest. We're going to look to see if we can group in either rows, columns, or boxes that many 1s in a group, because they'll be adjacent to each other and touching each other. That means some of the terms will be able to be thrown away. In this case, we can't take 16 of anything because there's some zeros in here and there's only 16 items at all. We can't do 8 because nowhere do we have 8 grouped, either in 2 rows. Of course, we could look at the bottom and the top row together, or in 2 columns, which would be this one and this one, or this one and this one, or this one and this one, or the last one and the first one. So we don't have 8 of anything anywhere. So now we would be looking for 4. Now the 4 could appear across a row, any of the rows, could appear down any of the columns, or it could appear in a box, you know, like 1, 2, 3, 4. So looks like there's a group of 4 right here. Looks like there's a group of 4 right here. Now this looks like there's a group of 2 right here. There's no more 4s that I see right off the top, but here's a group of 2. Now, we could grab that one as a set of 2, and that one as a set of 2, but we'd wind up with an extra term. We wouldn't have a real minimum. The reason is because these 2 are actually adjacent to those 2. So there is a group of 4 which does this. Now we look at every box we have and we make sure that it got some material that no other box has. So here's some extra ones in this box, so it's unique. This is shared, but it doesn't matter because we had some unique material. This guy right here and this guy taken together share a corner of that one and a corner of this one, but they have some unique material in them. This guy here shares a little bit here, but he also has some unique material. And this guy has this guy as unique. So all these boxes are necessary. So let's write down what equation this is equivalent to, which is the answer to our question up here. Go back to black. Y is equal to, we need the name of this box right here. We'll talk about who owns the boxes in a few minutes here, but let's just use some common sense on it. Do you notice that this box right here, both these two rows that this box is in, both are in a row owned by A inverted or not A? And they're also in a column that is sitting under not C. B changed, so B doesn't own all of those. And D changed, so it doesn't own all of those. However, not A and not C both do. Notice now that instead of 4 terms, we have a 2-term element because we were able to reduce down to 4 adjacent to each other. We got rid of the B term and the D term completely. Or, let's jump down to this corner again, this one down here. What about who owns this in terms of A and B? Well, A owns it, B changes, and across the top, looks like C owns them and D changes. So that would be AC. Okay, so let's try this box right here. Why don't you put in chat what you think the answer for that is? For that box right here. Who owns it in terms of A and B? Who owns it in terms of C and D? Go ahead and stick that in the chat. Okay, you either got it or you didn't. But if we look over at the left, who owns those rows? A, not B, not A, not B. It looks like the A changes, but the not B doesn't. So both those rows are really, that's what the area that not B owns. So this is not B. I'm sorry, this is not B, but it's also, I'm sorry, I'm looking at the wrong box again. It's this guy right here and this guy. He's not B. And notice C changes, so D remains around. Not B, D. Or we got this one box sitting out here that has 2 terms in it. Now clearly, if 4 terms reduced it to 2, 2 terms is going to reduce it to 3 elements because 4 terms would describe a single box. So we got to get rid of something here. We don't get rid of the C and the not D because they own the column it sits in. So we know it's going to have a C and a not D on the end of it. What we haven't looked at yet is who, on the left side, who owns these 2 rows? Well, A changed, so A is not an owner. B has it. So the last term is B, C, not D. So we took and wrote a minimum sum of products equation, which is, if we look at it carefully, we'll see there's only 4 separate input terms or products. And what we'll see is that very few inputs each, 2 inputs, 2 inputs, 2 inputs, 3 inputs, where over here we had 11 things ANDed together, 11 things ORed together, and each of those 11 had 4 inputs. So this is a bargain. This is good. Kernel maps, as long as you look for that overlapping new material thing, will always be guaranteed to generate you a minimum sum of products equation. So this is the best we can do. Now, what would have happened if we had, instead of doing what we did, grouped those guys and then grouped those guys as separate groups? That means we would not have this term, right? This would go away, but we'd have to replace it with a term right here whose name is not A, not B, D. And the one at the bottom is, this guy down here is A, not B. And D doesn't change. So we would have replaced this one term with 2 inputs with 2 separate terms, each of which have 3 inputs. So it really pays us to look and try to find those adjacencies and reduce the number of inputs we're going to have. Now, this would have been a rather hard problem to work using algebra. The Boolean algebra to come down and reduce and get this. You could ultimately do it, and that's one way we could check our work. But it's not going to be the easiest way to work that problem. Anybody have any questions about how we work that?
Could you ultimately factor out, if you went the wrong way, could you factor out the not B and D and leave it with not A plus or ORed with A, and that reduces down to the correct term?
Well, the answer is sort of yes. As a final answer, no, but on the way to the final answer, you can use parentheses, grouping, and factoring things out. So it's between these 2 terms, we see that the not A and not B do factor out. We also see that the not A and the A are going to basically be always true because they're ORed together. Since they're always true and they're ANDed with the thing you factored out, what's left is only the not BD, which was the original, as I recall, the original answer. So yes. So algebraically, we could see that and do it, but the order you put the terms in, whether it's this small up result or not, can also affect whether or not it's a simple thing to do. But all of them can be gotten to a final answer by using the algebra. I mean, it's what sits behind even doing this in the Kernel map. That answer your question? Actually,
Yes, thank you.
I think you answered your own question because you knew the right answer to it. Okay. I'm going to bring another one of those up. I'm going to try to not keep them all open. The other night when I was doing class, I had more windows open than I knew what to do with. Trouble is, I'm half blind here. When I come over here to open the window, I wind up opening something in the wrong stuff. Okay, let's just focus in for a second on the board. I can get it over here on the screen. Well, I guess I'm going to have to do it this way. What we want to look at is kind of the geometry of this thing and make sure we have a fairly clear picture in our mind of what lives where on the board. For example, if somebody said, I have an equation y equals A. Noam, can you tell me where I need to put my ones?
Yeah, in the 3rd and 4th column, in the 3rd boxes.
These guys?
No, the ones that are on the bottom.
The rows down here?
Yeah.
Okay. Columns are up and down, rows are across.
Okay.
Okay, so both these rows, just put a couple in there or put more?
You can, no, just down.
That's it?
Yeah, that's okay.
Okay, y equals A. Everybody agree with that? Anybody disagree with that? Give me a red light if you disagree with that, a green light if you agree with him. It's okay to disagree. He's not gonna be mad at you. Yeah, see, the problem here is y equals a says that all the squares represented by in the truth table that have a in them need to have a 1 in them. So this big chunk of 8 things put together, if I ever had that in a problem, I would say y is equal to a. What if somebody came up with the thing that said y is equal to c? Where is c? Rashana, can you tell me where c lives?
In the third port of the vertical.
Right here?
Yeah.
So down this column?
Yep.
Anywhere else?
And the one on the right of it.
You're exactly right. Okay, so that is, if I ever saw those 8 boxes marked together, we would say that's where C lives. Where would not B live? Basanthi?
Oh.
Let's have Basanthi on this one.
First row and last row.
Where's this?
First row and last row.
Okay, first row
And last row.
and the last row, and they're adjacent to each other, so that this and that taken together, if I ever grouped all them together, the term I would replace it with is y is equal to not b. What if I had this? We saw that if we have one term, we had, let's make a note of that. One term, we had 8 boxes. Now we have 2 terms, and our expectation is it's going to reduce down to 4 boxes. So where does AB live, Alexander?
The third row, all of them.
So this guy right here?
Yes.
You sure?
Yeah.
Okay. I wanted you to be sure before I drew my circle. Yes, he's right. Okay, AB, that's exactly where AB lives. And it was 4 in the box. How about if somebody wanted to know where not a, well, okay, let me do this. Not a D. Again, we're expecting 4 terms. Simon Lau.
It would be a box in the middle of the top and the top 2 rows.
So like these squares,
Yes.
you think?
Yes.
Okay. I'll draw my circle then. And that's right. It's in not A, D. Notice we have now 2 terms. So we would expect, if I add this up to 3 terms, so we want to have A, C, D, we should get a box that has 2 elements in it, or 2 boxes in it. So where is ACD going to live? Who am I going to ask a question of yet? Tatiana, did I ask you anything yet?
No, you haven't. So
I have now.
would it be in the 4th row, 3rd box?
We want A, C, and D. Now we can kind of triangulate in on it if you think about it. Let me take a different color here for a second. A owns all of this. C owns all of this. So you see we got this overlapping area now?
Mhm.
Now we got D. Which ones does D own? D owns those 2.
Yeah.
So it falls in the C box, it falls in the A box, it falls in the D box. So these 2 squares right here, that little grouping right there would be this equation. Everybody kind of catching on to what that is? Give me a green light if you're doing better than you were. Yeah, I thought so. Okay. Now let's look at a problem that I can, I think I need the whole thing, including the truth table for this. But let's assume that somebody had given us an equation which looked like this. How would we go about reverse engineering this chart back into the truth table? Well, we could divide this into sets of 4. We could then take and go 1, 1, 1, 1, because that's the way we would have pulled them out. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. The last row now, 0, 0, 1, 1, 0, 0, 1, 1. And then the second, or the very bottom row, 0, 0, 1, 1 again. 0, 0, 1, 1. So we could get back to our fundamental products. We get back to the truth table. We could actually evaluate this and get the full sum of products equation if we needed it. But if we were doing the reduced reduction form of this, we see that 8 of them are there. 8 of them are there. So in your head, figure out what y is equal to. Y is equal to not A, or these 2 rows are C. And then we'd have the equation we needed in order to look at this and say we knew, we kind of knew what was going on. We've kind of reverse engineered or center engineered. We could have any of the 3 and move. Now, what if I had this and I didn't have the Kernel map? Could I fill in the truth table? Well, let's see if we could. I'll pick a different color here. I'll pick red. What this says is everywhere A is a 0, I need to put a 1. So it's going to be the first 8. And this says anywhere C is a 1, I need to put a 1. It's here, so it's 0, 0. Well, I'll just write it without the zeros. It'll confuse you. So C is a 1 there. C is a 1 here. C is a 1 here. C is a 1 there. C is a 1 here. C is a 1 there. C is a 1 here. C is a 1 there. Now, if either or both are a 1, there should be a 1 in that line. So there's a 1 there, 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 1 there. There's no 1, so it's zeros. 1 here, 1 here, no zeros, a 1 and a 1. So we can just take, and by using what the equation says, get back to a truth table. So let me ditch this for a minute. Get another one. We have an equation, y is equal to A not B or C, D. We were given the equation. We want to find out, first of all, what the truth table is, and second of all, what the Kernel map is. Now I can go directly to the Kernel map. Let's do that. Where is A and not B? And how many squares is that going to be represented by? It's a 2-element item. So 2 elements is the result of a box or a line. So where is A not B? A not B is the entire bottom row. And that was grouped this way to get that term. CD is this column right here. And it was grouped to get that column. So we've completely exhausted this and said what the terms are. Now we should be able to go over to the truth table and write it out just looking at this, but let's not. Let's instead use this to go to the truth table. If A is a 1 and B is a 0, A is a 1 and a B is a 0 in that spot, that spot, that spot, and that spot. See that? A is a 1, B is a 0. Everywhere else, that's not true. If C is a 1 and D is a 1, here's a place where C is a 1 and D is a 1. Here's 1. Here's one. We already have a 1 there, but it's still there nevertheless. That's almost like the 2 overlap. We look over here and cheat. Yeah, they overlap. Here's a place where C and D are both 1s. So we could stick the extra missing zeros in. Here's the first 4. There's the second 4. There's the third 4. And here's the fourth 4. So we should be able to just put this in the Kernel map and they should hit the same spots. 0, 0, 0, 1. 0, 0, 0, 1. Bingo. 0, 0, 0, 1. 0, 0, 0, 1. Bingo. 1, 1, 1, 1. 1, 1, 1, 1. 0, 0, 0, 1. 0, 0, 0, 1. So we got to the Kernel map. We got to the truth table. We went from the truth table to the Kernel map. So we can move all around here. Now the teacher asked us to build this using 2 input NAND gates. So first thing I'm going to do is build a bus. So it's just going to be 4 vertical lines, which will turn into 8 vertical lines here in a minute. On our bus, this is A, this is B, this is C, this is D. Now, I'm going to go through an inverter. Now I'm going to draw the inverter as though it were really an inverter right now. Pull a line down from that. Down from that. That's a pretty droopy looking inverter, but okay, now we know we can build all of those out of 2 input NAND gates by simply doing this to the NAND gate. Tie the inputs together and just plug it in where that other guy is. We also have all our signals available now because this line right here is really named not A. This signal is named not B. This one's not C. This one's not D. Okay, that being a given, we need to now draw this circuit. We're going to draw it without regard to them being NAND gates. We're simply going to draw what's here. A 2 input AND ORed with another 2 input AND. So we draw an AND. We draw an AND. We draw an OR. And we label the output line Y. And we connect these together. Now, we know that the input to this guy has to go from A to not B on the other side of it. And this guy hooks up to C. And he hooks up to D. Now, in here, in order to make these NAND gates, the AND gate we drew either has to be, well, it has to get a nipple-looking thing or a little round circle on the end of it. The OR gates get those little circles, the little bumps, on their input side. So these are both Demorgan. Well, the second one is a Demorgan NAND gate. Oh, both of these are NAND gates, though. Now, in my picture down here, Anything that was drawn to look like an AND gate has to remain looking like an AND gate. Anything that looked like an OR has to be an OR forever. But we can convert it to a NAND by placing these little bubbles on the left side as inputs. So in order to do this, I can put a bubble here, but since I put one, remember the statement that says any Boolean thing that's doubly inverted is equal to the original. Since I don't want to change what the function is, I still want it to be ANDed into an OR. I just change that by putting a single inverter. I need to insert a second inverter. So I'll put a second inverter in there. Same thing down here. I need for it to be inverted, and I need a second inverter. Those two inverters cancel each other out functionally. This now looks like a NAND gate. These, of course, are built out of NAND gates. To make this guy look like a NAND gate, I've got to stick the two little circles on his left side. But if I do that, I have to put two of them. So if I do that, I put a circle. I need to put an inverter. I need a circle. And I need an inverter. Now I can come back through and I can say, well, anywhere I have two inverters in a row, I can get rid of them and still maintain the same sense. So if we just look at that with a little more detail, I have this guy inverted. He's going through an inverter, and I'm going to draw it like a regular inverter, into another inverter, which went into an OR gate on which we put a bubble. I won't draw the other side because it's identical. We have four inverters. I can just get rid of those two. I need to leave these two because I always have to have them in pairs, and that will make this a NAND gate and make this a NAND gate. This happens to be a Demorgan NAND gate, but that's just fine. So once I've done all of this, I now have taken and implemented this equation as gates. Specifically, this is a minimum sum of products equation implemented as gates. Now, how do I know it's minimum sum of products? Well, I don't from looking at it. I have to go to my Kernel map and make sure I got the biggest boxes and that each of them gained extra material by putting the box there. I don't see any overlapping things. There's no extra terms. So I can deduce that this is minimum sum of products. It's also implemented using a NAND gate. How many NAND gates did we need? We need 1, 2, 3, 4. Because we only have an inverted B. We don't need inverted A, C, or D. Now, as an exercise, we'll find we can go backwards from this to this, to this, and to that. So we can move in and among these four different representations of our equation in simple form. So we could take, and let's actually do one simpler. Well, it'll be as hard as that one is, but I'll draw it more precisely. Now you should be going right now, man, this is fun. This is what I come to school for. Anytime Bastien wants to do something fun like this, I'm on board. We can almost see the bottom of that, close enough. So you went and you found your dad's security alarm system and you took it apart. Wait till he finds out. And what you discovered was that there was two things ANDed together, ORed together. These were connected. Notice how this looks like the last circuit. That's intentional. There's a bubble here, a bubble here, a bubble here, and a bubble here. How do I know that? Because all three chips looked identical. Well, the way I know that is because they said 7400 on top of them as a part number, and that's a Nand gate. And then I went and I traced where these wires went, and I labeled them my own self. I called this A, I call this not B, I call this one C, and I call this one D. And I noticed that this thing went out and it was hooked to a solenoid, which caused the bell to ring anytime any of these switches went into their opposite position. So if A was asserted and the B was, so the two had to be together, but if they were, this AND gate kicked in and then it was ORed together. So either of those happening caused the alarm to go off. We'll call the output Y. Seen this before? Yes, we did, but let's make sure we know what it was. First thing we would do is we'd say, let's get rid of the NAND gate part of it because that's just going to make it confusing. Let's see how we could do that in the equation as opposed to just getting rid of them here. What we would see is we have A and B. Well, I won't even draw it that way again. I'll just go straight to the equation. This is A NANDed, that's what this is, together. So if I say Y is equal to A and B NANDed together, oops, actually B was inverted, wasn't it? B's inverted, and the whole thing is inverted. ORed with C and D. Inverted. But they're not really ORed. They're really NANDed, which is two things ORed together and at the end of it inverted, right? Well, no. If this is a NAND, the inversion happened on the way in. Now, looking at this, do you notice I got two things that are identical sitting on top of each other? Since I got two inverters, they can go away. So Y was equal to, get rid of the double inverted thing, A not B. That, of course, is ORed with, get rid of the double inversion, the CD. So let's put that into the truth table. Where is A not B going to be in the truth table? Who am I talking to at all? Nicholas.
Yes.
Where is A and not B in this truth table?
A not B, that would be the whole bottom row.
That's correct. Now, see, we already know the answer to this because we built the table that way. And while I got you, tell me where CD is located.
CD, that would be the whole third column from the left.
Right. So we can easily just taking what we had, and we already worked this problem in the other direction. We know we take this one to the truth table because this was our example. And we can take and fill in any of these three given any part. So if we start with a circuit, we can get to an equation, we can get to a Kernel map, we can get to a truth table. Okay, so let's take another practical problem here. See if I can get rid of this without having to load another one. Look at me, like I knew what I was doing. Ah, all right, hit the limit. On. Okay. There exists something called a 7-segment display. You've seen these before. Basically, there are 7 LEDs arranged as little lines, and they can independently be turned on. Let's say this guy is the A segment, the B segment, the C segment, the D, E, F, and G segment. Sometimes there's another one called DP or decimal point down here. But if you think about the way numbers are done with this, we start with 0. We basically take all the outside segments and light them up. A 1, we only take the right 2 most. A 2 would look like this. Oops, I'm giving you a 5 here. That's not a 2. A 3 would look like this. A 4, a 5, a 6, a 7, an 8 has them all on, and a 9. 9 looks like an upside down 6, except it doesn't have the serif part, doesn't have the carryover. Okay, so we got the numbers from 0 to 9. Let's assume we have a circuit, or we're building a circuit that can drive each of these LEDs. We're going to have a number, 0, 0 through 9, which is down to here, right? Which will tell us which number we're currently trying to display. Then we'll have a separate truth table for each of the LEDs. So we'll make the truth table for segment A, Y sub A. There'd be a Y sub B, a Y sub D, each of the elements, 7 of them up to G, I guess, because each of these inputs would drive different outputs through different circuitry in order to turn them on. But this is the common thing. Which number do we want to display? So let's look and see when A is turned on. And we'll put a 1 over here. A is turned on in the 0. A is not turned on in the 1. A is turned on with the 2. Turned on with the 3. It's not turned on with the 4. It is with the 5, the 6, the 7, the 8, and the 9. So there's 2 cases when it's not going to be turned on. But we have all these other possible things that could happen. It's possible that we could do a 10, 11, 12, 13, 14, or 15. But if we make our circuit right, those can never occur. So do we want to make those trues or do we want to make those falses? Well, there's one next to that guy. Well, let's think about it a second. We don't really care because we're never going to display them. Let's mark them as don't care. I'm going to put an X next to them. That's going to indicate don't care. Now we have to figure out what to do with them in the Kernel map. Let's fill in our Kernel map. First of all, there's the first 4, second 4, third 4, and fourth 4. 1, 0, 1, 1. 1, 0, 1, 1. 0, 1, 1, 1. 0, 1, 1, 1. Bottom row, 1, 1, X, X. 1, 1, X, X. And finally, the last row, X, 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 X. X, 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 X. Now the deal with the X's are, we have one choice we can make. One time we can make a choice. We can decide they're 1s or we can decide they're 0 on an X by X basis. And what we need to do is we need to decide whether they're 1s and 0s in such a way as to make our Kernel map solve as good as possible. So let's make a bad decision first of all. What I'm going to do is I'm going to make them all 0s. Yeah, I said don't write 0s. I'm not. I'm just writing that over the top of the X so we remember they're 0s. Now, what do we have that will combine in sets of 4? It's clearly no 8s. Well, here's one that will combine. That guy will combine. He got new material. He will combine. And then this guy up here could either combine with him or he could combine with him. Let's combine him with this guy just for the heck of it. Now every box got new material, so they're all needed. So let me write out the equation here quickly. Y is equal to, this box of 4 right here is called not AC. Or this little thing of 2 here is not A, B, D. This little set of 2 that across the top up here is not A, not B, not D. Remember, this is only going to light one of the 7 LEDs. So each of the LEDs has to have circuitry, and we need to make sure we minimize it as good as possible. And we have one more set of 2, which is A, not B. I need a plus in there, plus A, not B, not C. And if I got them all right, we have 3 3-term elements and 1 2-term element to equal the Y, which is our Y sub A. That's basically the equation telling us when the top of the segment, that segment A, should be lit. Now, hopefully I can get far enough back. I don't want to redo that again. If I can get there, here we go. Am I going to make it? Yes. And now let's assume for a second that I could decide some of those are 1s. What I'd probably do is make them all 1s. Now you wouldn't have to, but let's assume they all are 1s. 1, 1, 1, 1. Now the reason I did that, and these are 1s, the reason I did that is because now I've got a box of 8 that I can take here. I've got a box of 8 that I can take here. There's a box of 4 I can take here. And I can take all 4 corners together as a single box of 4. Dramatically reducing the terms. So Y is equal to, I'm going to cover the bottom 2 rows, so they're owned by A. Or the last 2 columns, they're owned by C. Or this center section right here. And the center section is owned by BD. Or the 4 corners, and the 4 corners are owned by not B, not D. And we're done. Look at that nice little clean equation there. By just picking them wisely. Now it could be that in our map we had something that was less obvious. Maybe we have X, 1s there with an X here, and then we got a bunch of 1s over here like that. Well, clearly it's going to be 3, that, and that set of 2, unless I can combine this. And then I would just pick this guy to be a 1. However, if, for example, I had an X here and an X there, I would not make them 1s. I would make them 0s because they add no value by combining 2 don't cares together. They just add an extra term that's useless. So sometimes I would look at it and say, I need the X to be a 1. Sometimes I need it to be a 0. Once it isn't a 0 or a 1, I can note over here what I finally decided it to be. But I have to remember that I can't change it from that point going forward because now it's locked into the equation. And since I can't produce these outputs anyway, or inputs anyway, theoretically, those don't matter what they are because it's an error if they ever appear. Anybody have any questions about that? Okay, let me grab another copy of this up here. Let's assume that I wanted to have 5 inputs. A, B, C, D, E. Clearly, I can't put that into 16 boxes because I have 2 raised to the 5th number of rows in my table. What is 2 raised to the 5th? Somebody just put that in chat if you know what it is. Should have come up with 32. Well, 32. How are we going to draw a set of boxes that are going to do that? We saw with 8, I could do a 2 by 4. Could I maybe do a 4 by 8? 4 by 8? This is going to work because I'm going to have some adjacency problems here because the ones that are here really are adjacent with these guys. So that's not going to work. Well, here's how we do it. What we're going to do is we're going to do 2 Kernel maps. And I didn't pre-print any of these, so you have to live with my sloppy writing for now. And we're going to say the entire Kernel map on the left is owned by not A. The one on the right is owned by A. So any equation I write that has an A in it, there'll be a 1 put on this plane somewhere. Any one that has a not A in it, it'll be on this plane. So obviously, if I were to take a box on this plane above a box on that plane, if I were to stack these up, that would put this A and the not A adjacent to each other, and the term could go away because obviously they don't own both layers. Together they do, but of course together they wash themselves away in an AND situation. How would I label the box? Well, I just start with B. Each box I draw would be not B, not C, not BC, BC, B not C. And this side of this box would be labeled identically. Across the top, not D, not E, not DE, DE, and D not E. And if we fill these out in order from a truth table, which has 32 lines, we're going to go 1, watch where my cursor is, 1, 2, 3, 4, 5, 6, 7, 8, bottom row, 9, 10, 11, 12, back up a row, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, skip a row, 25, 26, 27, 28, 29, 30, 31, 32. So that box right there is A, B, C, D, E. In the A plane, the BC row, the DE column. Remember, these rows and columns are labeled the same. So if we had a statement which said Y is equal to A, not B, C, where would those squares be in all of this? What squares are covered by that part of the equation? Well, the A says it has to be on this level. The not B says it has to be in the top 2 rows. And the C says that it has to be in the middle 2 columns, which means it's got to be those 4 squares taken together and circled. So it's A, not B, pick the rows, C, pick the columns. So those 4 squares right there are that. So we could do a Kernel problem exactly the same. We would copy all 32 into the chart, remembering to do the hop skip between the second and third column. 1, 2, 3, 4, and the same with the rows. Get the second row, jump to the third row at the bottom and come back up again. And same thing here in the second plane. We would label them in that order. So doing one of those is a little too much to do in class, might show up on a test or on a homework assignment, but I want you to see what would happen with 5 inputs. Suddenly we had to go 3-dimensional. Not only are we dealing with a height, in terms of columns, and a width in terms of rows, we're a depth in terms of which one of these 2 planes we're actually working on. So what would we do if we ran into 6 inputs? Well, we're not going to work one right now because it's going to have 2 to the 6th inputs, right? That means we're going to have 6 inputs, A through F, and we're going to have 64 lines in our truth table, meaning we need 64 boxes. We can't do 8 by 8 because if we did, we wouldn't maintain the adjacency. So what we're going to do instead, and I'm not going to label everything here, I'll just give some hint labels. We're going to build 4 Kernel maps. The first plane is owned by not A, not B. The second plane is owned by not A, B. The third one, you should guess, is owned by A, B. And the last one is owned by A, not B. Now, I'm not going to label everything here, it'd just take too long, but we know the top square on the rows is not C, not D. And we know that the leftmost column is not E, not F. Now we stack them up. Top, first row, underneath it, next one underneath, next one underneath. So that means as we're moving down the planes and we fill them in, we fill this one, followed by this one, followed by this one, and then back up a plane to this one. So now we have to do that little hiccup 3 places. As we're going across the columns, as we're going down the rows, and also as we go depth-wise into the planes. So we basically built the equivalent of a Rubik's Cube here, right? It's a 4 by 4 by 4. It's 4 deep. There's 4 sets of columns and 4 sets of rows. And same thing goes to the top here, would be divvied that way. So we can describe cells which are hidden inside the cube by putting them on the second and the third layer. And the same rules for finding where things fall into place. If you wanted to find where is the place that only E owns, you would have to go to every square in every plane that had an E and mark it as having a it would be a big 3-dimensional cube, which eats out the chunk called E. Anybody have any questions about that? These are kind of fun to do, but it takes too long in class to do one, so it's more of a homework assignment type of thing. Y'all are pretty good with that, I'm assuming. Okay, what if we have 7 inputs? Well, let me see if I can draw a black hole that we can all jump into here so we can all disappear. Okay, we can't do 7 dimensions or 7 inputs in 3 dimensions. We have to go into 4 dimensions. Now, I don't know about you, but I don't do my graphics that well in 7 dimensions. 3 is hard, or 3 dimensions is hard enough. And particularly when we're doing Kernel mapping and we're working on inner planes and things inside of a cube, trying to draw circles around them. Remember, our circles now have become spheres when we're working in 3 dimensions. So now we're doing something in an extra dimension, 4th dimension. While we could project them into 3 and possibly, we wouldn't be able to get the job done very efficiently. So we are back to algebra again. And that's really a problem, because if you think about it, that would be pretty horrible to have to do 7 dimensions, or not 7 dimensions, 4 dimensions using algebra, because we have 7 inputs, A through G. Now, of course, they could be named other things. But the fact we have 7 of them means that the algebra becomes rather complicated rather quickly. So instead of doing that, we're going to use a different graphic technique. Now, the technique involves a little magic. So those of you, that want to play the old magic card, this is your chance. And it involves you learning some algorithmic stuff in order to do them. But of course, with the Kernel map, we really learned an algorithm and then just kind of visually understood what was going on. What we're going to do is something called Quine-McCluskey. Now, you may hear it called Quine-McCluskey, and that's okay. The guy that, is that it? No, probably need a new one. Oh, here it is. Quine-McCluskey, which really is half of units, or part of Unit 6, where we're starting now. The guy, Quine, was kind of an eccentric, and he would pronounce his name both ways depending on where he was to confuse people. He himself never really pronounced it the same way, I don't believe, twice ever. So if you ever go listen to things, he's fairly modern. But if you look it up, you'll see that it's one of those things where there isn't really a correct pronunciation. Nobody knows what he thought it should be for sure. We use Quine in the class, so Quine-McCluskey is good enough for me. McCluskey, the other guy, he worked mathematics with this guy, and they both did some fairly significant things, but we're mostly interested in the method that we're getting ready to look at. Now, this method, years ago, let me see if I can open that up somewhere. And I'll post these PowerPoint slides. But way long ago, back in the mid to early 2000s, one of my students, Gautam Singh, who is a brilliant young man, went on to do brilliant things and probably still is. I haven't seen him in a while. But he decided that he wanted to put together a PowerPoint slide and make a presentation on the Quine-McCluskey method for us in class. And class was run differently back then because of the materials we covered. Were a little more mathematically based, so he was in the right place at the right time, and he put together these slides. One of the problems with the slides are he used a really old version of PowerPoint, and a lot of the features that were in it aren't supported anymore. So some of his animations or special effects don't do what they used to do, but they're really good, and what he put together works out very nicely for explaining the algorithm. So with my hat tip to him, ex-student, I'm going to explain to you how you do the Quine-McCluskey algorithm. Now, initially, for those of you that like to hear the algorithm in words, we'll talk about it in words. Then we'll do it using pictures. The words, while you want to note them, are not as useful to you as you think they are until we see the method, but then you can go back. I will give you this probably in the form of a PDF file, but possibly as a PowerPoint. I don't remember which one I have. And this one is a PDF, but I'm getting it from the website. So I'm not sure I can make that one available to you. So Quine-McCluskey, step 1. Let's define some terms here. First of all, we'll keep it this size. In a truth table, we have lines which end in ones. We gave those lines a name. We called them product terms. And it was the sum of those product terms that gave us our final answer. Well, they're still called product terms, but they also are known as min terms. And I've probably used that name for a bit. There is something called a max term as well, but we're going to use the min terms. they're equivalent to the fundamental products with one subtle little detail. And that has to do with the not, I'm sorry, let's not call it that. Let's call them the don't care states that we talked about in the last example. What Quine-McCluskey does for us, because we don't have the advantage of being able to see it in the same graphic way all at once, it's going to take care of deciding whether they should be a 1 or a 0 in an optimum way. And when they do that, they're going to require us to do some things in our method that are kind of, we'll look at it and say, well, I'm not quite sure why I did that. And we'll leave it at that for now because we're not going to do the math. Your discrete math teacher very likely will, and that's fine because this is something all computer scientists should ultimately know, which is why we're doing it. But we're, first of all, among all of the min terms we have, we're going to give them a second name. And the second name is something called an implicant. Implicant means that they imply a true. And the implicants include those min terms which are not only ones, but are also don't cares. So first thing we're going to do is go through our truth table and determine which min terms and implicants we have. But we're going to sort them in an order that's sorted by the number of 1 bits they have within them. So if I took the number 0001, I could say that that has 1 bit turned on, and I would sort it with all the other implicants that have a 1 turned on. If I said 0110, I would put that with all the ones that have 2 bits. Now, if I had 1110 and it was equal to in the truth table a 0, I would not use it at all, even though it has 3 bits. It's not useful to me because it's not really a min term. Its value result is not a true and it's not a don't care. So taking all my implicants and grouping them together by the number of bits they have and then arranging those so that I have groups of the 1s sitting next to the 2s, sitting next to the 3s, sitting next to the 4s, sitting next to the 5s. What I didn't mention to you is Quine-McCluskey is good for any number of input bits, not very useful with 1, but for large numbers. So if I have 7, 8, 9, 10 inputs, or even 5s and 6s where I don't want to work with 3 dimensions in Kernel, this is an ideal way to work those. As a matter of fact, for the 6s and 5s, I can check my answers with Kernel, and I can, with the lower numbered ones, I can check my answers with Quine-McCluskey. So I'm able to use it as kind of a way to check that I got a real minimum sum of products term. Of course, by the time I get to 7, 8, and 9 terms, I can only use Quine-McCluskey. So I'd have to use common sense then in equations and algebra to check the answers. So once I've gotten these into groups and the groups are sitting adjacent to each other, I'm going to look at every implicant in group 1 and compare it with every implicant in group 2. Anytime, this is going to be step 3, anytime I find an implicant that in the 2 groups, remember I'm comparing group 2 against group 3, anytime I find where they vary by a single bit, meaning every other bit is the same, but 1 bit is different, I know they're adjacent to each other. And I'm going to replace that term in a second column with a bit being replaced with an X. Now this X does not mean don't care. I know it's a little confusing, but in the literature, you're going to see X's used both places. Sometimes in one or the other, you'll see a star used to indicate it, but that has other overloaded meanings as well. We'll just use an X. Remember here, the X, if it's in the truth table, means don't care. If it's where we're working with prime implicants, it simply means that 2 implicants were the same as each other except for 1 bit. If we manage to get a bit to match, we're going to put a check mark next to both those implicants. Now, we're going to look to see if we generated two, let's call them, they're also called implicants, with X's in them that happen to match. Because if they do, we need to check them off as get rid of one of them because we have a duplicate. And we'll see that might be done here, might be done a little later, but we got to get rid of the duplicate somewhere. Now, lather, rinse, repeat, right? We're going to go back and do these steps over and over again, perhaps creating new columns with 2 X's, 3 X's, 4 X's, where things are the same except for one bit. As we go, we're adding check marks. Eventually, we'll make it through and nothing will compare with anything. We'll create no new data. At that point, everything that does not have a check mark next to it has been promoted to becoming a prime implicant. So the implicants that remain at this point, meaning they're not checked off, they still could be compared, but they don't match anything else. Those guys are called prime implicants. Now, it's from those prime implicants that we're going to try to represent and find those things which are called essential prime implicants. And an essential prime implicant is a prime implicant that is required in the final answer, meaning in the minimum sum of products, it's going to be one of those terms. And it may be necessary because it covers more terms than anything else does, and all the others would be covering duplicate terms, or perhaps it's essential because of the fact that it covers a term that nothing else covers, in which case we already know those are boxes we keep in Kernel. So even if we're working in 36 dimensions, we know that would be the same. We just don't have to look at all those dimensions graphically. We're going to take and keep the ones that cover the most columns and also have the fewest terms as our final remaining groups. We'll reject any of the implicants which are not necessary or which originally covered only don't cares. To accomplish that, step 1 here says make a prime implicant chart. We're also going to call that a table of choice. Give it 2 names. Across the top in the column headings, we're going to place all of the min terms for the terms that were true. We're not going to place any of the terms that were min terms that went in at the beginning as 1s because they were don't cares. Rather, we're going to remove them here as 0s. Now, the math underlying all of this will take care of picking the ones for us that were necessary. They will be covered correctly, but we don't have to deal with it. We just have to make sure in the very first step, we include them, and when we make the table of choice, we do not include them. And the rows will be labeled by any of the prime implicants we determined from step 1. So after hearing all those words, you're sitting there scratching your head, wishing that you'd seen this done before. But you'll have this writing to go back to as we go through an example if you wonder why are we doing that step. So let's do one now. Notice up here how the title gets kind of squashed. That's because in the old days, PowerPoint maintained their headings a little differently. Here we'll do one that's 3 input, because if we do, we can check it with a Kernel problem down here. 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1. So we can see we're going for a fairly simple answer. It's probably going to be a really easy answer, but let's see what got them cooked up for us here in the way of a thing. First thing, this first step said, we need to look at all of the terms and group them by the number of bits they have turned on. So the top row has no terms turned on. This second row has 1 term turns on. He also goes with the 1s. He's going to go with the 2s. He's going to go with the 1s. He will go with the 2s. He will go with the 2s. And he will go with the 3s. So we have something in all the groups except for the 0 group. We don't have a 0 group. So let's extract them and put them into their column. So I pulled out any that had 1 bit and labeled over here for my own remembrance that they were 1 bit long. These are the 2 bits. These are the 3 bits. Notice they're not taken out of in order here. Just as long as they're all grouped together, that'll be fine. But if you notice here, we had a 2 bit, then we had another 1 bit. So he had to get pulled into the 1 bits along the way. Now, if we look, he doesn't get pulled because he was false. But every other case, we didn't care about the ordering. We simply pulled them so all the 1s are together, all the 2s are together. Now, the next step we have to perform is we have to take each element here and compare it against each element there. Let me pull up a little window that I can write in for a minute and see if I can butt it up to that close enough. Yeah, maybe. Okay, so the first number we're going to compare is 0, 0, 1, and we're going to compare it against 0, 1, 1. Now, what we're looking to find is, are these off by 1 bit? Meaning, are they adjacent to each other in a Kernel map? Well, 0, it didn't change. This changed to a 1. That changed to a 1. So in the middle, they're different than 1 bit. So these taken together are going to become 0, x, 1 in a second column that we haven't drawn yet. And we're going to put check marks next to this guy and that guy. So they'll have check marks now next to them because they were combined. Take the same guy again. 0, 0, 1. We're going to combine him with 1, 0, 1. 1, 0, 1. Are they adjacent with each other? Yes, they are. Only the first one changes. So x, 0, 1. And we put check marks next to them. First one already had a check mark, but he gets another one. Or we'll just say the 1 was good enough. He needs to be compared again against 1, 1, 0. Are they different by 1 bit? No, they're different by 3 bits. So they get nothing put over in the other table. They also get no check marks. So we add no check marks. The 0, 0, 1 already has one, so we don't add another one. And 1, 1, 0 doesn't have one yet. So now we go to the second guy. 0, 1, 0. Compare him against the first guy. 0, 1, 1. Do they compare? You betcha. 0, 1, x. They both get check marks. Now we take the first guy, 0, 1, 0. We compare him against 1, 0, 1. Do they compare? No, all 3 bits are different, so they don't. Neither one of them gets a check mark. Okay, take it one more time. 0, 1, 0. And he compares against 1, 1, 0. Do they compare against each other? Well, yeah, the first guy is different. X, 1, 0. Now they get check marks. Okay. Now, if you notice, 0, 1, 0 had a check mark. Even though he didn't generate anything, he has that check mark. 1, 0, 1, he have a check mark anywhere? Yeah, he had one over here, so he has a check mark. 0, 0, 1 has a check mark. and 110 has a check mark. So if we'd done this, and if I could write over here, I'd be just putting the check mark and we'd see it, but I've duplicated the numbers. Notice that nothing in column 1 doesn't have a check mark any longer. So these guys right here, compared against these guys, all have picked up check marks. As a matter of fact, everything in this second group has already picked up a check mark, but we're not done with them because we have one more group to compare against. So this guy is done. They've checked and we've compared each against everything here, and we've generated some new data, these two guys and those two guys. So we'll have to deal with them in a few minutes. Now, in fact, let's deal with them now. 0x1 and x01 and 1x and x10 were a result of comparing the first row against the second row. Now we're going to compare second against third, so if we generate anything, we'll put them below another line because these two against each other generated all of that stuff. These two, bottom set, against them will be below the line because we used a different pair to do them. So let's take 0, 1, 1 and compare it against 1, 1, 1. Is that going to yield something? Yes, it does, x11. How about taking 101 and comparing it against 111? Well, that's going to yield 1x1. And the last one's 110 compared against 111. And he's going to be 11x. So now we've got 3 more terms here. And if you notice, the 111 was used, so he got a check mark. And each of the 3 top ones were used, so each of them got checked off, although they're already checked off anyway. So that means when we move on to the next page, these numbers become the ones we're interested in looking at. So now we've generated what we would call implicants, or I shouldn't say implicants, the next set of implicants. Notice over here we reflected all those check marks. So now what we need to do is we need to take what's in this group and one at a time compare it against everything in this group. So the top row against the first, top row against the second, top row against the third, second row against the first, second. And we're going to do the same thing. This time, if there's a 1-bit difference, the results in the next column will have 2 X's in them. Notice, and this is kind of an optimization here, that it makes absolutely no sense to compare this guy against anybody down here that doesn't have an X in the same position. So the only one he can really be compared against is this guy, because the X's have to match. This guy can only be looked at against that guy. This guy can only be compared to the last guy, and this guy against the first guy again. So if we do those comparisons, let's do one of them here just to see. 0, x, 1, which is the top one, against, the only one I can compare against is 1x1. Those compare off by 1 bit, so in the next column they're going to be listed as xx1. And so forth if we go through the whole thing. We're basically going to come up with this. In doing so, all of these guys did compare to something, they got checked away. And now we have some more to compare. You notice now that the top box contains xx1 and xx1. The bottom one contains x1x and x1x. That means really, if we get rid of duplicates, the top box contains xx1, and we're going to have to compare that against x1x. Notice that the x's don't line up, so we know we can't possibly make a comparison. So at this point, after we get rid of the duplicates, we're done. those will be the prime implicants that are left. And since everything over here is checked off, there are no more prime implicants. Let's look at that happen. Get rid of the duplicates. Those two remain, can't be compared, so they can't get checked off. We added no new material because of things that did get checked. Therefore, what's left must be the prime implicants. Okay, eyeball that page for a second there while I take a sip of my mighty fine coffee. Give me a green light if you like mighty fine coffee. Red light if you don't. That's good. Nasty habit. I'm glad you guys got some red boxes there. Okay. So now it's time to build the table of choice. What the heck is the table of choice? Well, that was the thing that lets us select the essential prime implicants. To do that, we need to build a table. I'll just sketch it out here for a second. Across the top, I'm going to draw them as boxes here. We need to put any of the ones in this table that were min terms, which were the original implicants that we cared about. And the only ones we put in are the ones that are a 1. Remember, if we had some don't cares, we wouldn't include them. So we know the first one here is got to be 0, 0, 1. 0, 0, 1. The second one's got to be 0, 1, 0. And we also know this is not A, not B, C, right? Third one here is 0, 1, 1. And then we jump down, we do the next 3 that are in here. So there'll be 6 columns when we're done. We have 2 prime implicants now, these 2 guys. So what we're going to do is we're going to label 2 rows in our table with their name. First one is XX1. And the second one was, what is it, X1X? Now, without giving anything away, what we're going to be looking for is where does that 1 line up with one of the things across the top? Because if it does, I can check that box as being covered by that element. We know the first 2 don't matter, so any box that ends in a 1 over here gets a check mark. Same thing, any box over here with a middle one turned on, this guy will create a check mark. Obviously, if the last 2 are on, they'll have a check mark above both. So let's move on to the table of choice, labeling it the way I just described. Here are our terms. Only the true elements are brought out. And here are the 2 prime implicants we discovered. What we're going to do now is put check marks in the column. We know there's a check mark going to go here because of this guy. Check mark here. Both of them have the last bit turned on. Check mark here. Check mark at the end. Obviously not this one, not that one. They don't get check marks. This guy will cover anybody that has the middle one turned on. That's this guy, not that guy, but this guy and that guy. So we can put our check marks. Now, this is the ultimate equation. We might be looking without that, in which case what we have to do is we have to say, in this table, find any column that has a check mark in only 1 row. Because if it's in that row by itself, whatever term is to the left is essential, because nothing else would cover that. This guy needs an essential. This guy needs an essential. Because we used up both our terms, we know we're done. But if we went on and checked again, we'd see that this guy, either term could correctly account for it. This guy requires the top one. This guy requires the bottom one. This guy requires either one. So when we're done, this is the final answer we derived. And we could check it by doing a Kernel map down here at the bottom. Let's draw that out and just do the Kernel map real quick. This is not A. This is not B. I'm sorry, this is A. Listen to me there. This is not B, not C. This is not BC. This is BC and B, not C. Our equation here says y is C. Well, where's C? C is in those two rows. Where's B? Well, B is in those two rows. So if we just use the final equation, it matches what we originally extracted from the truth table. And we know the groupings would have been those four and those four. And those four describe precisely these two elements. So we could check it with Kernel after having done it with Quine-McCluskey. Obviously, Kernel is much faster. Actually, I didn't draw my box big enough there. It includes that one. But the checking with this doesn't really take that long when you start to do these. Okay, let's move on to the next problem. This problem has some don't cares in it. Remember I said we'll call them X's when they're in the truth table. But when we're using them in the table of choice, or we're using them to derive the table of choice, the X here just simply means 1 or 0. Doesn't mean don't care. It means it specifically, it doesn't matter. It's really I guess it's kind of a don't care, but it's a way to indicate that 0 and 1 in that position is just fine, as opposed to we don't care what it is. Okay. Think through in your head what the first step is before we look. Here's our truth table. What is it we're going to do first? Okay. You're going to find all the rows that are either true or don't care, and you're going to count the number of bits in that row so that you can work with it. Let me bring up a Kernel map for that. Let me get rid of this for the moment. So I'm just going to copy this off of here for the moment and see if we're good. 0, 0, 1, 1. Let me set it in 4s again. Zero, zero, 1, 1. Zero, zero, 1, 1. XX, 0, 0. XX, 1X. Now, I think it would do us some benefit to go ahead and fill this into the truth table or in the Kernel Map, since it's only got 4 inputs, so we can, as we go along, look at what's happening to us. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. XX, 0, 0. X, X, 0, 0. XX, 1X. X, X, 1X. Now, what we'd really like here is to get a minimum number of terms. And in doing that, we see all sorts of opportunity here. For example, we could combine that 4 right there and that 4 right there and that 4 right there to make 3 groups of 2 terms each. We also could take, and that would be assuming we made everything ones. Let's assume we make this row right here all ones. We could take just that row and just this box. Now instead of having 3 sets of 2 inputs, we have 2 sets of inputs, making these would be awfully nice if these guys wound up as zeros. But there's another one that's kind of nice here. This guy and that guy, meaning if I made this guy a 1 and those zeros, then I don't have to deal with those. I still get the same number of terms, and yes, there's an overlap. So we're probably going to be able to say both of those are valid answers. One of them has this box plus that box. The other one has this box plus that box. Quine-McCluskey should help us with the 1s and 0s in this area and with this guy to make sure that we reduce ourselves down to something that's got 2 terms in it at the end, and each of those terms have 2 inputs. We don't want to wind up picking all these as 1s, wind up with an extra box for nothing. That's important. Give me a green light if you see that. See, that would be a redundant box of data. We could do it, we could build it, but it would cost us money, time, and heat, and circuit complexity, and power. Okay, so this guy has 1 bit turned, or it's true, he has 1 bit. This guy has 2 bits. This guy has 2 bits. He has 3 bits. He's a don't care, so we're going to put him in with 1 bit. 2 bits. Remember, we wouldn't see this if it were 17 degrees of freedom. He has 2 bits. He has 3 bits. And he has 3 bits. And he has 4 bits. There are no 0 bits. So we're going to have some 1s, we're going to have some 2s, some 3s, and some 4s. It could be that you had some 1s and some 3s. If you did that, you would not compare the 1s against the 3s. The 1s would never get check marks. 3s wouldn't either unless there were some 4s. It turns out, though, we have some 1s, 2s, 3s, and 4s. So we'll have plenty of adjacencies. Remember, we're going to group all the 1s together, basically draw a line, put all the 2s, draw a line, all the 3s, draw a line, and the 4s. We'll compare all the 1s against the 2s, all the 2s against the 3s, and all the 3s against the 4s, creating a new column over here which has 1x in the position. We have to create another column that'll have 2 x's, another column 3 x's, until we can't create more data, and we then go back and pick up all the ones that required a check mark or didn't have a check mark and couldn't be compared to anything else as being the valid ones that remained. Okay. Now you should be rubbing your hands together. Ah, man, we're going to work a problem now. Yes. Okay, let's move ahead. Here's our groups. Remember we said we'd have some 1s, some 2s, some 3s, and some 4s. Kind of the eyeball check that we did what we said we were going to do. Notice, here's one of the don't cares. We used it. Even though it doesn't evaluate to true, at this point we want to tell the system that it potentially could be true, so it will help us resolve things. Now, sitting down and doing the comparisons is tedious. You know, it is a time-consuming thing. But believe it or not, this is a much easier way to write a computer program that emulates this algorithm than it is to write one that emulates Kernel mapping. Kernel mapping turns out to be a little more difficult to write valid software programs against it. And I've seen lots of successful programs that can work against Quine-McCluskey, even Quine-McCluskey with, 23 inputs. And by the time you get those large inputs, that's when you need the computer assist anyway. You wouldn't sit here and do that by hand. That would be much, much too complicated. And when we get to many, when you get to 10 or 11 or 12 inputs, sometimes you actually don't even work the problem to a unique solution. Sometimes you work separate problems, each of which is a minimum sum of products, and the results of which are usable and buildable, although not optimum, not the best you could have done. And that's a design decision. How much engineering do you do until, how many digits of pi do you calculate till you're done? We know you'd never be done. So let's pick, 10. Be done with it. Okay, so we're going to take the top guy, compare him against all 4 of these. Will he match anything? Well, he matches the first guy, 0, 0, 1x. He matches this guy, 0x, 1, 0. He does not match this guy. He does not match this guy. And he would get a check mark, and the 2 guys he matched would each get check marks. Let's assume all that was done. We would have generated a new column. Now remember, what's in this set is the things between 1 and 2. What's in this set are the comparisons between 2 and 3. What's in this set are the comparisons between 3 and 4. Now we're going to do the same comparisons. Again, we can only compare where the x's line up. So he could be compared against that guy and this guy, but nowhere else. And then you're looking at the remaining bits to make sure that only one changes. If only one changes, you both get check marks, and the next column gets an element with an X in that position. So the next column would have something with 2 X's in it. Everybody good with where we are? Give me a green light so I know you haven't abandoned me. I would be very sad if you abandoned me. You might have a couple abandoneers here. Well, I can check my scroll. See, the system keeps track of when you leave and when you're here, when you move your mouse and that sort of stuff. And nobody just sits there not moving their mouse. And it also, when I ask for participation, I know if you didn't participate. Okay, so here we go. Let's do this column against this column. We can do it by hand again, but let's not. Let's look and see what he did. Okay, we've got our comparisons. Everything got checked off. So we're not done. Now we have to check, and again, we'll check anywhere where these match in terms of axes. But I want you to notice with this, there's duplicates. These 2 match, those 2 match. So there's really only 2 things to match up here. Same thing in the bottom. There's only 2 here, only 2 here. So will this guy match anywhere in the bottom? The answer is no, because the X's don't line up. And both sets of X's would have to be in the same place. So he's not going to get a check. Let's check this guy. Is he going to match anybody? We need X's in the 2nd and 4th place. There aren't any. So he's not going to get a check. So both of those are going to become prime implicants, as will these, because nothing matched them. So we have 4 prime implicants. Let's see that happen. Notice we got rid of our duplicates. Now we have our prime implicants. What do you think the next step is? Oscar, what's the next thing we're going to do?
I'm not really sure. I'm kind of lost here.
Okay. Kyle, what's the next thing we're going to do?
I'm lost as well, sir.
Okay. Somebody who's not lost, get on and tell me what the next step is.
Do we create our table of choice?
Oh, who said that? I heard both of
Me.
you. That's Nicholas? Okay. Or
Yes,
William?
William.
William? Okay, both of you said that? It was
Yeah.
perfect. I'm going to put you guys on tour and you can be singers together. Okay, yes. We're going to build the table.
That's a bad
of choice.
idea. I'm bad at singing.
We'll let him do the singing. You can do the signing or something for me. Okay,
Perfect.
Here we go. Here's our table of choice. What we did is across the top, notice we only put the ones that have 1s next to them. On the left-hand side, we put all of the prime implicants. Prime implicants, true values. Now we're going to look at these and see what gets covered. Let's just anticipate. We're going to cover anything that starts with 1s. Only the last guy starts with 1. So we know there'll be a check mark right there. Check. Only the middle 2 are 1s. It's this guy, and this guy. So there'll be 3 check marks. Check, check, check. This guy, first one is a 1, third one is a 0. Well, it's not that, not that, not that, not that. None of them match this guy. Now, some news for you. This is the guy that covered only don't cares. He can be thrown away. So we just got rid of a two-term element. It's exactly the same thing we did in Kernel. We noticed that box over there would have been all X's. Well, the algorithm took care of tossing him out. He's not useful anymore. This guy covers anybody that starts with a 0 and has a third 1, which is all of them, up to, well, not the last guy, but the first 4. So let's put our checkboxes in. Now, what we're looking for is any that are covered by only 1. This guy is. This guy is. So we know that this element right here has to stay around. His name is not a C. So not a C is going to be in the final answer. We know A, not C, is going away. Now, in the other columns, we have multiple things covering them. Now, this gives us a choice. And remember, we had 2 possible answers the way we worked our problem earlier. One of them is the fact that these are already covered means I could use this guy to pick up that one. Or I could use this guy to pick up the last one since those 2 are already covered. But I don't need both of these. Either one is an okay answer, either AB or BC. They're both valid. They both take care of covering this remaining 1. Whether they cover these additionally or not doesn't really matter. We know we need this guy because he's the only one that can cover these. So let's take a look. We have either, remember I said the bottom row down here is not AC. Y is not AC, or we have AB, which is the top guy, or we have BC. We don't have both of them. So either of those answers are correct. What's important here is notice they're both sum of products that have 2 input, 2 terms. They're equal number of terms, equal number of grouped together. So they're equally good to build. You would pick the one that fit your circuit the best in terms of your design. We can prove that from looking at the Kernel map, the same picture I drew earlier. We must have this box here. His name is AB. I'm sorry, yeah, listen to me. His name is not AC, which is the first element. Then we said we could either have this guy, which picks up one of the don't cares, and his name is BC, which we said. Or if we didn't want to pick him up this way, this extra one, we could pick it up with the whole row. And if we did, his name is AB. So the Quine-McCluskey did exactly what we needed it to and demonstrated to at the end that we had 2 possible solutions, either of which is just as good. Anybody have any questions about that? Everybody see that the redundant equation is okay? Okay, let's move ahead. Now, I don't know about you, but I can't read that. But nevertheless, there's a truth table there. If you zoom in and you look at the 1s and 0s, I think you'll see that I don't think this one has any don't cares in it. We'll look and see for sure. Those are all 1s. Yeah. He wanted to demonstrate here that you could do a 5 input as well. So we'll go through the exercise without looking at the data too much. We divide it into the number of 1s. In this case, the 0 group has no 1s, also it had a value itself, so it's in there as the 0 group. Here's the 1s. Here's the ones that had 2 inputs, 3 inputs, 4 inputs, 5 inputs. And again, if we had none with 2, we would not compare these against those. It'd be impossible for them to match in the first place because they got different number of bits. And so at least 2 bits would have to change. So they must always be adjacent if you're going to do that. Otherwise, they don't get processed. We're going to compare all 0s against all of these, each of these against all of those, each of these against all of those. We're done. We'll have a group which covers this group, one that covers this group, one that covers those comparisons, one that covers those comparisons, and then finally at the bottom, one that covers the final comparisons. That's not a big deal or hard to do. It's just something we need to do. So we're going to go through it, and we're going to wind up with comparisons that look like this. Again, we just replaced the place where there was a 0 in one and a 1 in the other with an X. As you see, this is just time consuming. It's not any harder to do. Wouldn't matter, this truth table could have 10 inputs, we would still be doing the same thing. It's just a matter of visually doing it, getting it done, and not making mistakes. You can see how this would be prone to mistakes. We do it again. Notice in this one, although we're not going to do the work, when we compared against this group against that, we actually generated these three elements. These three did not match when we tried to compare those against them. These had matched because they got check marks from above, but these did not get check marks. That means that these three terms are going to be prime implicants. They will appear in the table of choice. But we still have some more work to do because we may have some that have further reduction. Notice in here also there may be some duplicates. So we'll clean that up. We'll do the comparisons here. We do that, reduce it down to the no duplicates. We now do the comparisons. The comparisons got rid of, they all compared. We got check marks everywhere. But now we're left with a single term that has duplicates. Obviously, no further boxes when you're only comparing two things. So the one that's remaining must be a prime implicant because it can't compare against anything. So XOXOXO, sounds like I love you. XOXOXO here is going to be the final prime implicant. It's not B, not D. Over here, we still have these. This is not A, B, C, D. This is B, C, D, E. This is A, B, D, E. Those three plus that one need to move into the prime implicant table. Table of choice, here it is. We put those three answers. Notice I put the one with the most X's further up. It's going to get the best payback in terms of number of inputs. So we try to use it first if we can. Now I'm going to list in the table everything that was in this table that had a 1 at the end of it. And again, if any of them were don't cares, we wouldn't include them. Here they all are across the top. Now I have to mark the ones that got covered. I'll put check marks. This guy covered all of those, and he covered all of those. The second guy covered the last two. This guy covered this as well as that. And the final guy covered these two. Now, by observation, we can see that the top one is necessary. So we know for a fact we're going to need to have whatever the top one is. So it's not B, not D. We also know that the bottom one is necessary. It's the only one that covers that term. So that's not A, B, C, D. Now, this one is necessary. And he's necessary because he's the only one that covers that term. He's A, B, D, E. Now, who have we covered? All of those are covered up to here. He's covered because this guy covers both of them. Those are all covered. And those are covered, right? So this guy, the BCDE guy, is not necessary. He was covered by this guy and he was covered by that guy. Do you see that? That this guy covers terms that are already covered. If we'd picked him first, we'd have to come back and see that he's really, if we do a Kernel map, he's one of those boxes that's not new material. This box with that box completely cover his box. So he's unnecessary. But this is our final equation we'd be looking at here. And if we make the equation ourselves, not B, not D, not A, B, C, D, and A, B, D, E. There is our equation we've extracted from it. We don't need the fourth term. This is helpful because we can visually see that that's not necessary. Always get rid of the ones that have a single value first because we know they are required. So we managed to pick out the right terms for that. That was less than painful. Now here's another one. If you notice there's a Kernel map, or I'm sorry, a table of choice listed here. This is the last 2 pages of this handout. Gautam's plan and my plan for you is you're going to do this one at home. And on Wednesday night, you're going to bring the answer. Don't send it to me or give it to me in advance, and don't share it with other people necessarily. Try to work on your own so you learn how to do it, not how to copy. And if somebody asks you for it, shame them a little bit because they shouldn't. But we're going to turn it in, and we have a procedure we have to follow to turn it in. It's the same procedure we use for taking tests. And I want to make sure that everybody is up to the task because it involves a little more than just turning it in. And I occasionally get people that don't quite know how to use their computer. And so we'll try turning this homework assignment in. And it's real simple. You're just going to do the Quine-McCluskey equation, minimum sum of equation from this. And it should match, if you do this also, and I would do it as well as a Kernel map problem, it should match the results you get by doing a Kernel map of the same. He gave you 2 pages to write on, so you can either print them out and work on it or put them in some editor where you can edit, graphically and make sense to yourself. I would probably print them out so I could look at it and understand what I did later. Beware with this, there is an unknown value right there. So when you're doing the table, remember this goes into the original count the bits stuff, but this line is not included in the table of choice, and it will make a difference. So that's a homework assignment for you. It shouldn't be too much of a problem. You should be able to work your way through that and not have any serious setbacks. I think given that you get this set of handouts, and I'll either post this in Blackboard or I may put a link to it on the website. Not sure. If it's on the Blackboard, I've noticed that you can't select and use the link as a hot link. I'm looking into getting them to change that so they become hot links for you. But you'd have to type in whatever I give you, and it's more than 10 characters, so be careful. It should return you a document that looks exactly like this one if you run PowerPoint on it, or something similar. Or it may be, this is a PDF file, so it might be a PDF you can just view. I don't remember. We'll have to see what I have posted out there. Okay, I want to do one more little review thing here. And I think I can do it on this. I want to review with you some of the algebra that we went over that I know a couple of you were having a little bit of trouble with. Everybody remembers we worked in regular thing, commutative law, the associative law, and the distributive. We covered those. I'm not going to go over those again. Even in Boolean, they're simple enough. One just says we can do pluses and multiplication type things in either order. One says we can bring them outside of the parentheses. It doesn't matter. Associative says the order we do things in when we have like 3 things doesn't matter. And we had duals for those. Does everybody remember what a dual is? A dual is going to be a way that you take a Boolean expression. So we say y is equal to a or b. And by following, well, let's actually do it the other way. A or b is equivalent to b or a. That actually is the commutative law. And we said our dual for this is something that is proven true by virtue of the fact we followed the rules, not because of the fact we proved it to be true. And the rules were take anything that's an or and change it to an and, take anything that's an and, change it to an or, take anything that's a 0, change it to a 1, and anything that's a 1 and change it to a 0. And so in this case, we changes the ors to ands. And that would make the dual correct. We did that for the associative, distributive, and commutative. As a matter of fact, when we talked about Demorgan's law, we said A or B, where that entire thing is inverted, which is a NOR, that's equivalent to A, B. Now, these are easier to write if I can draw over the top of them, but what we said here is that if we take two things, OR them together, and then invert it, we get the equivalent of ANDing two inverted things together. And what we said about that was, that's an interesting thing to look at, because that means that if this is a NOR function, so is this. We just call this a Demorgan. I'll put an ED on the end of it. Demorgan NOR gate. Notice that this looks like an OR and this looks like an AND. That's why when we're drawing those pictures, you know, if we do this, why when we draw a gate that looks like this, and somewhere else we draw a gate that looks like this, I say to you, when you turn this into its NAND gated version, don't change the AND-ness of it. What we're trying to do is keep it an AND. In order to keep it an AND, I put a bubble and an inverter there, meaning it still functions exactly like an AND does. This guy, what I'm saying is I want it to function like an OR because that's what it was doing in the circuit. So if I put an inverter here and an inverter here, which is invert the two inputs before you OR them together, then these guys need another inverter over on this side to doubly invert them. Now, in this case, this is not a NOR, this is a NAND. This is a NAND. But this is the demorganized version. I'll put D on there so I don't have to write the whole thing out, demorgan. So if I'm writing an equation and somebody had given me something that says y is equal to A or AB or CD, using the rules that we've said is I would just draw this out to be exactly what it is. Something ANDed, and they're ORed together. The order of the ORs don't matter, remember? I would draw an OR. This is bullet with little curved edges on it. I didn't draw it very well. And we have one more thing ORed with the result of all of that. So here's my other thing. And there's another OR gate out here that both of those are ORed with. So that is the circuit. But when I tell you what I want you to do is turn it into NAND gates, what I'm basically doing is telling you, leave the circuit's picture alone in terms of what they are. This stays an AND. This stays an AND. This stays an OR. This stays an OR. Put enough inverters on its nose so it stays an AND, which means two of them. Put enough inverters on his nose so it stays an and. That makes him a NAND, but there's an extra inverter now floating around out here. These ORs, put an inverter on this side, but you can't put one, put two of them. One is the bubble, another is an inverter. Now when you're done, if you wind up with two inverters in the middle, which you would right here, get rid of the two because you don't need the two. You already have an inverter here, and they cancel each other out, leaving this an AND gate and that an OR gate. We're not trying to change the behavior. We're trying to change the implementation. So we talked about this being a NOR gate here, so we could redraw these as NORs. But in the case of a NOR, the natural one looks like an OR. The Demorgan one looks like an AND. So we need its dual. What's its dual look like? Well, follow the rule. The rule is we're going to invert something that over there was ORed together instead of the ANDed together here. It's going to be equal to. So this is a NAND, and that's truly the NAND function. Notice that after you've ANDed it, invert it. If the function we want is an AND, we'd have to invert that output twice. If we wanted to leave it an AND, we turn it into an AND gate by doing that, which would make the chip an AND, but we'd throw another inverter in so that it maintained its AND-ness. Same thing with the OR gates. On the inputs, if we don't want the inverse coming in, if the original picture had the original A and B coming in, and we need to invert it to be an input to a NAND gate or a Demorgan NAND gate, we need to throw two inverters in. So this remains a simple OR function of those values. Okay, I want you to do some studying before Wednesday. Do the homework assignment. I will post the assignment as just a link. You have to remember what to do. I probably won't post it with any words other than the last 2 pages of the handout are the homework assignment. And we'll turn it in during class on Wednesday so you can learn that procedure. Anybody have any final questions or words or anything that I forgot to cover tonight?
How exactly are we just supposed to have the answer on us next class?
Yeah.
Okay.
Just know what it is. Anybody else have any questions? That was a good question, Zachary. Okay, then I guess I will call class over. You guys go get a snack. I'm going to go get a snack, and I'll throw this coffee out since you guys said I shouldn't like it. And I'll see you guys on Wednesday night. Have a good one.
See you Wednesday.
Good night.